Okay, and that last example we did from chapter 3. Remember, this is the one where I was saying just because we're in forces doesn't mean we can forget what we learned in chapters 1 and 2 in terms of kinematics. So example 3.5.2 says, starting from rest, an ice skater whose mass is 54 kilograms pushes the boards with a force of 130 newtons west and moves 0.704 meters. He then moves at a constant velocity for 4 seconds before he digs in his skates and starts to slow down. When he digs in his skates, he causes a net force of 38 newtons west to slow him down until he finally stops. A wants us to determine the acceleration of the skater in all 3 portions: when he's pushing the boards, just after he stops pushing the boards, and when he starts to slow down. And then B says, how far does he move in total? So you'll notice here I've drawn the situation already with all of our given information and broke it down into all 3 sections already. Okay, so because the acceleration changes in each portion, we have to look at each individual section as like its own problem. So we're going to have to solve for the acceleration here in that first part where we know he starts with an initial velocity of 0 and then moves a certain distance. Okay, then we're going to have to solve what the acceleration is here when he's traveling at a constant velocity for his 4 seconds. And then finally, what his acceleration is when he's exerting this force of 38 newtons in the west direction to slow him down until he stops. Okay, so for the first part, for I, let's look at a free body diagram of our situation. Okay, so we know our guy's mass is 54 kilograms. Okay, and we know the force of gravity is acting on him, and because he's on a horizontal surface and not accelerating up or down, there's a force of normal that is going to be equal and opposite to that force of gravity. Now, he is exerting a force of 130 newtons on the wall. Okay, but remember, we're looking at him as the object. So even though he's exerting this force in this direction, he is going to feel the reaction from that applied force. So he is going to feel the force that he applies onto the wall of 130 newtons, except it is going to push him to the east, right? He feels the same magnitude in the opposite direction. So he's applying that force west, but he's going to feel that force moving east. Okay? We're ignoring friction in this case, okay, because he's on ice. We're going to assume that we're ignoring friction. So there's no other forces that are acting on him at this point in time. So if we look at the F net acting on him, then the only force that contributes to that F net is this applied force. And we'll recall, any F net equals a mass times an acceleration. So we can say that the applied force that he feels is going to simply be equal to his mass times his acceleration. And to solve for his acceleration, we're just going to look at taking this applied force and dividing it by his mass. So we take our 130 newtons in the east direction, and we divide it by his mass of 54 kilograms. Okay. And that gives us 2.407 meters per second squared. And remember, that direction is the same as that applied force. So we know that it's moving east. So for part I, the acceleration that he experiences is 2.41 meters per second squared in that east direction. Okay. Now we're going to take a look at the second portion here. So after he accelerates at this rate, he travels a distance of 0.704 meters, excuse me. Then from that point on, he travels at a constant velocity. So remember that a constant velocity means something for us in terms of the forces acting on him. Constant velocity tells us that the net force acting on him then is 0. Remember, just because there's no force acting on him doesn't mean that he can't continue to move at that constant velocity. So because we know F net is 0, remember, any F net is equal to a mass times an acceleration, and because his mass can't be 0, in order for our F net to be 0, that means the acceleration has to be 0. So we know for the second portion, he actually is not accelerating. Okay? Constant velocity means no net force, means no acceleration, right? And that's Newton's first law that says we can either be moving at a constant velocity or be still unless there's some net external force acting on us. Okay? Last but not least, we're going to take a look at this third portion. So this third portion, again, let's go and draw a free body diagram for it. So, just as we did in the first portion, we know there's going to be gravity and normal that are going to be equal and opposite to one another in this situation. Okay. And then it says he's exerting a force he's digging in his skates, which exerts a force of 38 newtons west. So in this case, he actually feels the force slowing him down in that west direction. So the force that he is applying on the ground is the force that slows him down in this case. Really what it's doing is it's increasing the friction between him and the ground. And remember, friction always acts opposite his motion. So even though he continues to move in this direction, because of that applied force going west, we know that his acceleration is also going to be going in that direction. Okay? And then just as we did in that first portion, we can solve for the net force acting on him. You'll notice that because we're ignoring friction, there's no other forces acting on him at that point in time. So the only force that is contributing to his net force is this applied force. We also know that any net force is a mass times an acceleration. So we can now again solve for the acceleration by saying that applied force is going to be equal to his mass times his acceleration. And then the acceleration is simply going to be the applied force that he applies to the ground divided by his mass. So we get this 38 newtons west divided by his mass of 54 kilograms. Okay. And that gives us 0.7037 meters per second squared west. So for our sig figs is 3. The acceleration during that third portion is going to be equal to 0.704 meters per second squared in the west direction. Okay, and that's part A. So now that we have all those accelerations, we can think about all the variables that we now have over each portion in order to solve for that displacement. Okay, so I'm just going to add in here in each of our portions what we now know about the acceleration. The acceleration here is 2.41 meters per second squared east. The acceleration over this portion is 0 meters per second squared. And then we know over the last portion that his acceleration is 0.704 meters per second squared west. Okay, so now we need to go and solve for how far he moves. And in order to do that, we know he's going to be moving to the east here over this entire motion. So let's just say any quantity that acts east is going to go positive for us. Any quantity that acts west is going to be negative. Okay, so how far does he move? Because his acceleration is different. Again, remember back to kinematics, we can only use those equations when his acceleration remains constant. So just as we had to break it up to solve for the acceleration, we're going to have to break it up to solve for his displacement over each portion based on his acceleration, and then add those total displacements together. Okay, so for part B, we actually don't have to do anything for that first portion, right? For that first portion, they've told us that the displacement over that portion is 0.704 meters. Okay, so we're going to leave that for a second, and we're going to go and look at the second portion and trying to determine its displacement. Now notice here, we have no acceleration. So remember, when we have no acceleration, we really don't even have to use our kinematics equations. Remember, our kinematics equations are present for when acceleration is present. So when your velocity remains constant, remember what that allows us to use is that average velocity formula. So we can say that the average velocity is going to be equal to the displacement over that second portion divided by the time, right? And then we can then rearrange to say that that displacement over that second portion is going to be this constant velocity that he's traveling at multiplied by the time that he is traveling at that constant velocity. Now we have the time as 4 seconds, but what we don't know is we don't know what this constant velocity is. So we have to solve for that. In order to solve for that, we are going to have to go back and use situation 1. Because notice, we have an initial velocity, we know how far he travels, and we know his acceleration rate over that distance. So what we can do is at this point right here, after 0.704 meters, is we can find what that final velocity is at that point in time. That final velocity then becomes the constant velocity that he travels at for the next 4 seconds. Okay, so we're going to go back and look at situation 1. We have initial velocity, we have acceleration, we have displacement, and we want final velocity. So the kinematics equation that we are going to choose in this situation says that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Okay, remember, we don't have an initial velocity. We know it's 0. So the final velocity that we're solving for ends up being equal to the square root of 2 times the acceleration times the displacement. So we can go and get that final velocity now using what we know. 2 times our acceleration rate over that first portion, remember, was 2.41 meters per second squared east. So we're going to plug that in as positive 2.41. And then our displacement was also in the east direction, so that also goes in as a positive value. And it was 0.704 meters. Okay. So when we simplify, the square root, we get 3.39328 meters squared per second squared, which gives us a final velocity when we take the square root of that of 1.842 meters per second. Okay, and because it's positive, we know that's traveling in the east direction. Okay, so now we're going to take this velocity that we solved for, and that becomes the velocity that he's traveling at a constant rate for that 4 seconds. And that's what now allows us to solve for how far he moves during that second portion. So we know that average velocity is this final velocity of 1.842 meters per second. And it's going in as positive because it's east. And we're multiplying that by 4 seconds. Okay, so his displacement over that portion ends up being 7.368 meters. And because it's positive, we know that's in the east direction. Okay, I'm just going to add that in here for that first displacement because we know that as well. All right, and then last but not least, we're going to go and look at the third portion. So again, we know his acceleration. We know what the final velocity is, and we're trying to determine, again, how far he travels. Right? We want this distance here over that third portion. So we want displacement, we have final velocity, we have acceleration, we need something else in order to use a kinematics equation. Well, remember, what we solved for was the final velocity at this point. He then travels at a constant velocity for the next 4 seconds before some acceleration starts to slow him down. So we also actually know at this point what his initial velocity is. His initial velocity is that average velocity or that final velocity of the first portion that we solved for. So we do know 3 variables, and we're looking for the fourth, which is that displacement. So again, notice we have the exact same variables that we had in that first situation. We have initial velocity, we have acceleration, we have final velocity. This time we're just looking for the displacement. So we use the exact same kinematic equation again, as we did in this first portion to solve for the final velocity, that says final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. This time our final velocity is 0. Right? So we get 2 times the acceleration times that displacement we're looking for is equal to the negative of the initial velocity squared. So that displacement that we're looking for is equal to negative of the initial velocity squared divided by 2 times the acceleration. Okay? So that initial velocity was this average velocity that we traveled at. So we get the negative of 1.842 meters per second all squared. Remember, that gets plugged in as positive because it's east. And then in situation 3, our acceleration was 0.704 meters per second squared west. Remember, we defined east as positive. So when we plug in that acceleration now, we have to plug it in as a negative value. So I'm plugging in the acceleration as negative 0.704 meters per second squared. Okay. So 1.842 squared works out to be negative 1.3572 meters squared per second squared over 2 times our negative 0.704 is negative 1.408. Okay, your negatives are going to cancel. And we get a displacement of 0.9639 meters, again in that east direction. So now you have all three displacements, and we can go solve for what the total displacement of our skater is by just simply adding those three displacements together. Okay. All three of them are going in the east direction, so we don't have to worry about switching any of those directions. We're simply going to add them together. So we get 0.704 meters plus 7.368 meters plus 0.9639 meters. Sorry, I just realized something didn't look right there from what we did in class. This answer is incorrect. So I'm just going to go back and switch this again quickly before we get the total displacement. Sorry, that was a calculator misstep on my part. So sorry, 1.842 squared works out to be negative 3.3929 meters squared per second squared divided by our negative 1.408 meters per second squared. There we go. Again, your negatives are going to cancel, but that gives us the displacement that we got in class of 2.4097 meters east. Okay, that looks right now. And now we can add that proper displacement in. And we get a total displacement of 10.4817 meters east. And we had three significant figures. So to answer part B, we're just going to round it to 3 sig figs. It says his total displacement over this entire motion was 10.5 meters in the east direction. Okay, so remember, even though we're in forces, don't forget everything you learned in kinematics, because really forces is what produces motion. So we can use what we know from forces to determine some things in kinematics. Okay, and that's it for chapter 3. This is Wanny signing off, and may the force be with you.